So today we'll do one problem on these vibrations and dynamic part for a particular structure. So everyone write down the question. Let us test a free vibration test is conducted. Write down the question. A free vibration test is conducted on an empty water tank. Empty water tank. A cable attached to the tank applies lateral that is horizontal force. Horizontal force of this is actually horizontal force of 72.95 kilonewton. And pulls the tank horizontally by by 508 mm. The cable is suddenly cut and the resultant free vibration is recorded. And the resulting free vibration is recorded. Okay. At the end of 4 complete cycles, the time is 2 seconds. That is at the complete of 4 cycles. So the oscillations they have recorded at the completion of 4 cycles. The time is 2 seconds and the amplitude is 1 inch. And the amplitude is 1 inch. That is how much? How many meters it is? 1 inch means 25.4 mm. 25.4 mm. Okay. Okay, from this data, compute the following. First one is damping ratio. Damping ratio. Second one is natural period of undamped vibration. Next, stiffness. Next, the weight. Damping coefficient. And finally, number of cycles required. Number of cycles required for displacement amplitude to decrease to think to decrease to 5 mm. To decrease to 5 mm. To decrease to 5 mm. Okay, so this is the question. Please bear with my handwriting. You just write down on your own in your notes or somewhere. So this question, a free vibration test is conducted on an empty water tank. The cable attached to the tank applies a lateral horizontal force of 72.95 kilonewtons. So you have applied 72.95 kilonewtons at the top horizontally to this water tank. That is, you are using some cable and pulling it, the tank horizontally, and it was pulled by 508 mm. It was pulled by 508 mm, and then suddenly the cut. You have cut that particular wire. Then after cutting that wire, they have recorded the results, and after 4 cycles, it was observed that after 4 complete oscillations, they observed that it took 2 seconds for 4 oscillations, and the amplitude is 25.4. That is 1 inch. That is 1 inch. That is 25.4 mm. From this data, you have to calculate damping ratio, natural period of undamped vibration, stiffness, weight, damping coefficient, number of cycles required for the displacement of amplitude to decrease to 5 mm. That is the last one is, see, you can understand that. So how many cycles required? You have to calculate number of cycles so that the amplitude will come back to 5 mm. Initially, it was after 4 complete cycles. Initially, it was as 25.4 mm. Okay, so we will calculate all these parameters for this particular, and the diagram for this one is it is a free supporting water tank. So this is the water tank, and it is supported here like this. So for this one, we are pulling it. You are applying a force, or you are pulling it with 72.95 kilonewton, and then you're releasing it. Then obviously, when you pull it and release it, it will start oscillating, and the details of this water tank you have to calculate. Here, the damping, actually, I told you damping can be also roughly calculated in certain cases. The formula for calculating the damping is, it is called a free vibration test. In the free vibration test, the damping ratio can be determined. Xi equals to 1 by 2 pi j ln of xi plus j. So this is the formula to calculate the damping ratio. And in terms of acceleration, also you can write the formula. In terms of acceleration, also you can calculate, but we have the displacement over here, so we will proceed with this one. So in place of acceleration, you will get two dots over here like this. Okay. So since we have displacement, we are using the displacement formula. Okay. So this is the formula. So from this, you can calculate here the displacement. What is the displacement we have? Xi. We got the displacement for amplitude of four complete cycles, right? So for 4 cycles, that is J, you can say for 4 cycles, we got a displacement of 508 mm. Okay. So if you substitute this in the equation, you will get the damping ratio Xi equals to 1 by 2 pi into 4 cycles ln of Xi is how much? 508 divided by Xi plus j is what? This is the amplitude here. And it was found to be how much? 25.4 mm. Right? So this is going to be 25.4 only. So if you calculate this, how much is this value? Tell me this value. 0.119. Yes. 0.119. 11.9%. So this is the damping ratio, and 9.9% is the dampness in the particular structure based on the amplitude and displacement. We have calculated the dampness in the property. This actually, this percentage of damping for concrete and steel, we have the standard values. But since for this particular structures, it is a free vibration, and we have amplitude and the data is available, we have calculated the damping value for this particular force of 72.95. So here this is the first one. The second one is what? A natural period of undamped vibration, that is t, natural period of vibration is how much? It is quite easy. This you can calculate. How much is the displacement that we found? The displacement cable is suddenly released. The horizontal displacement was 508 mm. Okay, and how much is the maximum amplitude? It is so the time taken is 2 seconds, right? Sorry, uh, 2 seconds to complete 4 cycles. So 2 by 4, right? You have 4 complete cycles for the completing 4 complete cycles in a time of 2 seconds. So here the time period is how much? 0.5 seconds. Okay, and stiffness. Now the stiffness formula we know that stiffness K equals to force by displacement. That is how much we have 70. 95 by displacement is how much? 508 mm. 144 kilonewton per mm. You can write per mm. You can convert it. Okay, then next one is weight. Weight, that is so here to calculate the weight, we have to find out the angular frequency. You have to calculate the angular frequency, and using the angular frequency, we can calculate the weight. Here to calculate the weight W, first we have to calculate the angular frequency of Young cycles. That we know that the angular frequency formula is 2 pi by t. So here this is going to be how much? 12.57. 2 into 12.57 radian per second. So radians per second. So angular frequency will be calculated in radians per second, and the relation between this angular frequency and the mass we have. So stiffness K equals to mass into angular frequency of nth cycle. From this we can calculate mass equals to stiffness K by angular frequency. So the stiffness value we know 0.144 divided by 12.57. So this is going to give you a value which will be 0.0009 1 0.000091, right? Oh here, so here the weight equals to 0.00091 into 9.81 meters per second is the acceleration due to gravity that you have to multiply over here. 9.881. This 9.81 G is in what are the units for this? This is in meters per second square. 9.81 meters per second square. And this we are having here by mm. So this will be divided by 9.81 is there, and for this one 0.0091 it should be multiplied with 1000 because that is in mm. So here second square and then it will convert to meter and that will be cancelled. So into 1000, 10 power 3. So this will give you 8.9 kilonewton. Okay. So we have calculated the time period. We have calculated the stiffness. We have calculated the weight. And next one is it clear? Can I go to the next slide? Any doubt? Yes, can you tell me, is there any doubt? Okay, next slide. So here in this one, next point is what we have to calculate. Next one is damping coefficient. So damping coefficient of here, it is indicated with C, and this formula is given as C equals to psi of 2 root over K M. Root over K M. So this is going to be the time coefficient. From this you can calculate, the xi values and the other values. From this you can calculate 0.119 into 2 into root over K is how much? K is 0.144 into mass. So we have here mass equals to this one 0.0091. That if you multiply by 1000, it will come to meters. Into 10 power 3. So what is this value? Zero 0.086. Okay, it is a ratio, so there will not be it's a coefficient. It's a coefficient, you don't have limits for this. Okay, and the final one is here, that is what will be the number of cycles required for the displacement amplitude to increase to decrease to 2 to decrease to 5 mm, right? So here this one frequency, here you will be using this the same formula. This is the free vibration calculating the damping ratio. So the damping ratio formula, whatever we have used, 1 by 2 pi ln of xi by the same formula here. You are calculating the amplitude. So what should be the amplitude? That is to reduce it to 5 mm. Okay. So here you can take this G onto the left side, and then you can calculate the J value. So this is going to be 1/2 pi xi ln of xi by xi plus. So from this 1/2 pi into the percentage of the value what we got is 0.119 ln of this value. The displacement how much we got? 508 divided by, and how much you want to reduce to 5 mm. So substitute 5 over there. So what is the value you will be getting? So how many cycles? J value from this. So ln of 508 reduces to 5 mm. And it should come to 6.18 seconds. 6.18 seconds. These are the values. So it requires 6.18 cycles to come back to this cycles required, so that it will come to 5 mm of displacement, maximum displacement. So we have calculated this. And when it is pulled with a force of 72.95 kilonewton, then the displacement it was found as 508. So based on these two parameters, if you draw the free body diagram of this, based on these two parameters, this is the displacement delta, and the force that it is pulled with 72.95. All the other data have been calculated in this manner. Okay, and you can then analyze it. You can plot a graph. Its natural period of vibration. You can plot this after every second. You can plot the graph, and when it comes to the normal position, you can plot like this, and you can say that at particular point it will come to a stop. Okay, so for it to reach to 5 mm, for it to reach the amplitude to reach to 5 mm, it took around 6 cycles, 6.19 some cycles. So some more cycles, if you take like one or two cycles, it will come back to its normal position. Okay, so these things can be estimated. These dynamic analysis, the behavior of the structure can be estimated. So with